Hello everyone, my name is Yenji Betaria Sonata Tampubolon. My ID number is 4213121024. So I am from Physics Education Study Program at Middle State University 2021. So now I will explain about final exam basic nuclear physics. Number 1 questions. The stone owned by Sambo turns out to be made of the one core of element P204 emitting alpha particles with a half-life of 120 years to become the stable core of element K. The ratio of P nucleus to K nucleus is 5:11. The mass of P nucleus is 140 grams, with 1 amu is equal to 1 times 67 times 10 to the power of 27 kilograms. So find A, the age of the Sambo amulet stone, B, when the time needed for the comparing factor of K nucleus and P nucleus to become 5:11 for the Sambo amulet stone. So we can see is given is T half P204, it's equal to 120 years, and P per NK is equal to 5 per 11, and P is equal to 140 grams. Is A TP and B is T when and K per NP is equal to 5 per 11. So we can see with the solution, with the formula is NTP is equal to NOP times half it's to the power of T per T half. So we can see NP 204 it's equal to 5 per 16, it's equal to 120, it's equal to 43 times 75 grams. So we can find with the solution is T is equal to 0 years. The next is B problem. So NK is equal to 5 per 16 it's times 140 it's equal to 43 times 50 grams. So NOK it's equal to 140 grams minus NOP it's equal to 96 it's equal to 25 grams. The next steps is we will use the formula is NK per NOK it's equal to half to the power of T per N2. So we can find the T it's 137 it's equal times 4 years. So now we can move to number 2 questions. So the questions is the water in the Minahasa reservoir turned out to contain hydrogen gas and its isotopes, namely H1, H2, and H3. For the water alone, it has a water discharge of 10 to the power of 6 meter to the power meter cubic per second and has been occurring since 10 years ago, which is stored in reservoirs. Isotope H2 has a power of 0 times 0.0024 percent of the total H isotopes. Meanwhile, isotope H3 has a slightly large part than the part of H2. These isotopes are used as fuel in fusion-type nuclear reactors with reaction equation being H2 plus H3 long hetero He4 plus n, where 2 times 1041 U with the MH3 is 3 times 116 U, and MHE for it's equal to 44 times 0024 U, and the last is N is equal to 1 times 187 U. So determine is A, the total energy that can be generated from the water in the reservoir, and B, if the electric power consumption of North Sumatra province in 4 GeV, and the nuclear reactor efficiency of 0 times 65. When will the total energy supply from the water in the dam run out? So we can see the solution is given is key is equal to 4 times 10 to the power of 6 meter cubic per second. H2 is 0 times 0,0241% H2 plus HT is HA 4 times plus N. MH2 is equal to 2 times 141 U, and Mn is 1 times 0087 U. So it's asked as A total, and B, if P is equal to 4 GeV, D is equal, N is equal to 1 times 75, then when it's 10. For the 8 problems, NH2 is equal to 0 times 0,0241 per 100 is equal its times is 4 times 10 to the power of 6 meter cubic per second times 350 times 300 times 5. So we can find with the formulas. So MH2 in water is 3 times 0,2 times 10 to the power of 13 kilograms. So NH2 is 1 times 5 times 10 to the power of 10 meter cubic per U. And the next is NH3. So we can see the formulas. MH2 in the water, it's equal to 3 times 0,4 times 10 to the power of 10 grams. So we can find the NH3 is equal to 1 times 0,069 second times 10 to the power of 10 m cubic U. The next is energy release per reaction. So the formula is A is equal to delta mc quadrant. So delta m is equal to 0 times 196 U, and E is 16 times 74 MeV. So the total is with the formula is number of moles H2 energy reaction plus number of moles H3 energy reaction. So we can we get it. The final is 4 times 44 times 10 to the power of The next is B problems, and with the n it's equal to 75x, it's equal to e, it's equal to 75 per 100 times 4 times 44 times 10 to the power of 11 MeV. So E is equal to 3 times 33 times 10 to the power of 11 MeV. So P out is equal to 4 times 10 to the power of 9 W is, and T is P in per P out. So we get T is equal to 1 times 332 times 10 to the power of minus 11s. With the 1 MeV, it's equal to 1 times 6 times 10 to the power of minus 13. So the next is we can move to number 3 question. So the question is, raffle stick is a stick made from juju trees and is considered sacred by the Mario tribe on Tex Island. During its lifetime, the tree obtained isotope C40 from the process photosynthesis. The proportion of isotope C14 compared to isotope C11 12, it's 1 times 2 per 10 to the power of 11. The mass of the raffle is about 4 times 1 kilogram, and at the time of its sampling, 1 times 5 grams was detected with an activity or decay rate of 340 kbq. So determine is A, initial activity of C14 when the jojo trees were cut. B, why and how the comparison of C14 and 12 is constant when a tree is alive. And the last is C, what is the age of raffle sticks? T epsilon is for 1,400 years. So for number 3, so problem is given is NC14 per NC12 is equal to 1 times 2 per 10 to the power of 11. M stick is equal to 4 times 1 kilograms. M cuplican is equal to 2 times 5 grams. A is 340 kbq, and S is A O C 14, B Y and C 14 per NC 12 is constants, and C testing if the C14 is equal to 1 is equal to 6,040 for 100 years. So with a problem, we can see the formula to find A is A0 times half to the power of T per 3T half, and A0 is lambda times N0. So we get lambda is 1 times 0.8 times 10 to the power of minus 4, and MC14 it's 4 times 92 times 10 to the power of minus 11 kilogram. So we can see A0 it's 1 times 6 times 10 to the power of 9 dpm. The next is B problem. So the ratio of C40 to C12 remains constant in living organisms due to the continuous exchange of carbon with the environment through processes like photosynthesis and respiration. In the atmosphere, C40 is formed by the interaction of cosmic rays with the nitrogen, and it then gets incorporated into carbon dioxide or CO2. Plants take in the CO2 during photosynthesis maintain a consistent ratio of C14 to C12 as long as they are alive. When the organism dies, it's no longer exchanges carbon with the environment and the C14% start to decay while the C12 remains stable, which allow for the dating of the organism based on the remaining C40. So the next is C problem. So is as a statistic. We can see the formula to find A is lambda times n. N it's equal to A per lambda. So we get 3 times 140 48 times 148 kilograms. So for the N0 is 148 times 48, and the last is T, we get minus 1969 times 13.6 seconds. So the next is number 4 question. So the question is, there are two kinds of radioactive nucleus materials, P and K. Initially, the comparison factor of these three nucleus material is 3 to 7. The half-life of P material is 5 days. After 70 days, the comparison factor of the three materials becomes 7 to 3. So find the A, the decaying half-life of key radioactive nucleus, and B, the comparison factor of both radioactive nucleus materials after 120 years. When do both radioactive nucleus material have the same comparison factor? With the solution is given is NOP per NOK is equal to 3 per 7. T 10p is equal to 5 days. T is equal to 70 days, and NP per NK is equal to 7 per 3 days. So it's as is T half 8 key, and B and P per NK after 120 days, and C is T when NP is equal to NK. With the A problems, when we want to get T half key, we can see the formula is NP per NK it's equal to NOP times half to the power of T per T half P. It's per NOK times half to the power of T per T half key. So we get T half key is equal to 5 days. For B question, so the formula is NP per NK it's equal to NOP times half to the power of 120 per second per NOK times half to the power of 120 per seconds. So we get NP per NK, it's 3 per 7. For C problems, NP per NK is 1, so NP it's equal to NK. So the formula is NOP times a half to the power of T per T half P, it's equal to NOP times half to the power of T per T half K. So we get T it's 0 days. So the last is number 5. Number 5 question. So the question is A. They are two kinds of the well-known nucleus models as a liquid drop model and the cell model. Explain both and find the advantages and disadvantages of each model. So we can see the liquid drop model. The liquid drop models likens the nucleus to a drop of incompressible fluid. In this model, consider the nucleus as a collection of nucleons or protons and neutrons bound together by a strong nuclear force similar to molecules in the drop of liquid held together by cohesive force. So the advantages is number 1 is simplicity. The model provides a straightforward and intuitive ways to understand nuclear binding energy and certain nuclear reaction. Number 2 is binding energy calculation. It successfully explained the binding energy of nuclei through the semi-empirical mass formula, accounting for volume energy, surface energy, Coulomb energy, asymmetry energy, and pairing energy. And the last is fission and fusion. So this is useful in explaining nuclear fission and fusion process. And the last is disadvantages. So number 1 is no individual nucleon behavior, is that does not account for the behavior of individual nucleon or quantum mechanical effect. And number 2 is magic number, fail to explain the stability of nuclei with specific number of protons and nucleons magic number. The next is cell model. The cell model describes the nucleons in terms of individual nucleons occupying discrete energy levels, much like electron in an atom. Nucleons fill this level according to the Pauli exclusion principle. So the disadvantages is number 1 is magic number. So it successfully explained the extent of magic number where nuclei exhibit extra stability. Number 2, individual nucleon behavior accounts for the quantum mechanical behavior of individual nucleons and their specific energy level. So number 3 as nuclear properties, so helps in understanding nuclear spin, parity, and magnetic moment. And the next is disadvantages. Number 1 is complexity, so more complex mathematically and computationally compared to the liquid drop model. And number 2 is empirical adjustments, often requires empirical adjustments and does not easily explain collective behavior like nuclear deformation and rotation. So the next is big question. The question is, in view of the nucleus model, have spin parity and the magic number that the terms has effect to atomic cell to explain these terms and find the two solved problem is it. So we can see the spin. Spin is the intrinsic angular momentum of the nucleon or nucleus. It's quantized and can be either an integrate of half-life integral multiple of the reduced Planck constant or h bar. So atomic cells is the atomic physics electron spins contributes to the total angular momentum and affect the magnetic properties of atoms. The last is nuclear cells. Is in nuclear physics, the spin of nucleons affect the overall spin of the nucleus, its energy levels. The next is parity. Parity is a property that indicates the symmetry of the wave function of the particles of the system under spatial inversion or flipping the spatial coordinates. With the atomic cells, parity influence the selection rules as atomic transition and the symmetry of electron orbitals. And with the nuclear cells, nuclear states have defined parities with the critical in determining the allowed transition between energy level. And the last is magic number. Magic number are specific number of nucleons or protons or neutrons that result on highly stable nuclei due to closed nuclear cells. The next atomic cells in so in atomic physics, magic number correspond to closed electron cells leading to inert gases with highly stability, and the nuclear cells in nuclear physics magic number it's 2, 8, 20, 28, 50, 92, and 126 indicate closed nucleon cells leading to exceptionally stable. So guys, this is all my explanation. If have any mistakes, I apologize. So we have when I have a mistakes, we can discussion on the commenter. See you.